Hello, welcome to our channel. So today we're going to discuss about mapping of instructions. So as you know that we have two types of mapping. One is direct mapping and one is indirect mapping. So before entering into our concept, those who are watching my channel for the first time, I request you to please subscribe my channel and please share my videos to your friends and well-wishers. Okay, so let's get into our concept. So direct mapping. So what is the difference between direct mapping and indirect mapping? So let's take a best example, general scenario. Okay, for example, if you want to, if your friend called you and asked for your address, okay, for example, if you say that come to follow this route A, okay, come to this landmark and call me. So he will call you, and again you will say come to this landmark, and again your friend will call you. You will say that come to this landmark. There he can find your address. Okay, so that's indirect mapping. Why? Because you are saying first one landmark, and next you are saying landmark B, and next you are saying landmark C. There, your friend can find your address. Even though there is a straight route to your house, but you are saying indirectly. Okay. Whereas direct mapping, you can straight away go to that particular landmark. Okay, so that you can find your friend's address like that. So direct mapping in the sense, at that particular address, at that particular opcode, you get the data present in it. Okay, right. So indirect mapping, so it points out to some other route. You go to that route, and it points to some other address. You go to there, and it points to some other address. There you can find the data. Okay. So opcodes of interaction, opcodes of instruction. So here we have total 5 types of instructions. One is add, and, LDA, load accumulator, STA, BUN, branch unconditional. Okay, right. So if you see 0000 is for add, 0001 is for and, okay, and 0010 is for LDA, 0011 is for STA, 0100 is for BUN. So if you see here, we have a control storage. Okay, so everything is stored here. For this, for add, we follow an add routine. For and routine. For LDA routine. 0011 is STA routine, and for branch unconditional routine. Okay, so if you see, as you know that 0 to 11 is for address, 12 to 14 is for opcode, and 15th bit is, as we know, it's for whether it is a direct or indirect. Okay, so if you see the mapping bits here, you can see the 4 bits, which is marked with X. Okay, so here you can take the first 2 is 10 and 010. So with this, we can have different combinations of having add routine, and routine, LDA routine, STA routine, and BUN routine. If you see 10, if you use 0000 in the place of 4x, XXXX, then we get add routine. Okay, so 0001 will get and routine, 0010 will get LDA routine, 0011 will get STA routine, 0100 will get BUN routine. So in this way, we can map our instructions. So mapping from the opcode of an instruction to the address of the micro instruction, which is the starting micro instruction of an execution microprogram. Okay, so if you see the machine instruction here, we have an opcode and we have an address. So here we are combining the opcode. Actually, 0 to 11 is address, 12 to 14 is opcode, and 15th bit is whether it decides with direct address or indirect address. Okay, so but we are combining it with 4, that is 1011, which is an opcode, and mapping which is 0. These 4 is linked with 4x. Okay, 00. This is micro instruction address. Okay, so 1011. So 1011 means, so 1011 00. So mapping function implemented by ROM or PLA. So this mapping function is implemented by ROM, read-only memory, or PLA, programmable logical array. So anyways, we'll discuss these ROM or PLA in our last unit. Okay, so here we have an opcode. Here we get a mapping memory, which is a ROM or PLA. Then we have control address register for controlling, and finally the control memory. So we already discussed about control memory in our previous videos. You can go to our previous videos and you can check it over there. So and the next one is microprogram example. This is the most important. So how these instructions are put together. Okay. So and how the computer configuration we get. So as we know, we have a memory of 2048 into 16. Okay. So and here this is the address, right? Okay. So for denoting address, obviously we have an address register. So which is of 0 to 11. So that's what, right? So 0 to 11 is for address, and 12 to 14 is opcode, and 15th bit is our direct address or indirect address. Okay. So here 0 to 11 is our address. So here we have a multiplexer. So 0 to 11 is AR, and again I'm taking 0 to 11 as PC. So PC is a program counter. So program counter which always points to the current address. Okay. So you can see the link for address here. Okay. So multiplexer. Here we have a data register. So data register, we know that 0 to 15, that means 16 bit. Okay. So 0 to 15, that is data is of 16 bits. Okay. So depending upon once we get the data present from that particular address. Okay, so then we can perform arithmetic units or logical operations or shift micro operations. So that is a micro program example, right? So it's a group of micro operations. So we can perform arithmetic micro operations or logical micro operations or shift micro operations, right? So for that reason, we need an arithmetic, logic, and shift unit, and we have an accumulator. So accumulator is a temporary register 0 to 15. Okay, so you can see how there is a combination here. And finally, we have CAR, that is control address register, which is of 0 to 6, 7 bits, and SBR. So SBR is subroutine register 0 to 6 again, 7. And your control memory is 128 into 20. Okay. So if you see, memory is 2048 into 16, whereas a control memory is control unit. As we know that in the main unit, we have a control unit which is a small part which occupies only 128 into 20. Okay. So but anyways, we have a link between these two from memory. Finally, it is connected to control address register. How it is controlling? So that's what we have seen here. So opcode, mapping memory, ROM or PLA. Then again, control address register and control memory. Right. So that's what your micro programming example is. So machine instruction format. So what is machine instruction format? As we know that. Your address is from 0 to 11, and opcode is from 11 to 14, and I bit is from I bit is 15th bit. So 0 to 11, 0 to 11 is address, but here the machine instruction format will take 0 to 10 as address. Okay, that is 11 bits. Normally 0 to 11 will be address, but here it is taken 0 to 10, that is 11 bit, and from 11 to 14, that means 11th bit, 12th bit, 13th bit, and 14th bit. So these 4 bits occupies the opcode, and 15th bit is I bit. So here I decides whether it is a direct addressing or indirect addressing. So if we see the simple machine instructions, as we said that we have 4 values for the opcode, that is 0, 1, 2, and 3. Okay, so opcode 0 stands for 0000, and 0001, 0010, 0011. So 0000 is nothing but your add symbol, that is micro instruction. As we know that EA is the effective address. So branch 0001, if AC less than 0, then EA tends to PC. So the first, what is add here? So first we should know the effective address, right? So M of EA. So M of EA stands for effective address, which is added with accumulator. The result is stored in accumulator. Okay. So, and coming to branch. Okay. So what is branch here? So branch means going to one place, that is jumping. So if AC less than 0, if your accumulator value is less than 0, then effective address is sent to program counter. So EA tends to PC. Now we are storing it. So which one is stored here? The value present in the accumulator will be stored in the memory address of the effective address. So M of EA. So AC tends to M of EA. And finally exchange. Okay. So AC to M of EA and M of EA to AC. It's a vice versa. So this is called exchange. So these are all sample machine instructions. So first one is add, second one is branch, third one is store, and fourth one is exchange. So if you see the micro instruction format, so micro instruction format in the sense here, as we said that for address is of 7-bit address. So AD 7. So BR is a branch field. So branch field occupies 2 bits, and CD is conditional for branching, which occupies 2 bits. And here we have 3 types of fields, that is micro operation fields. We call it as F3, F2, and F1. So F3 occupies 3 bits, F2 occupies 3 bits, and F1 occupies 3 bits. So if you count the total number of bits here, so 7 plus 2, 9, 9 plus 2, 11, 11 plus 3, 14, 14 plus 3, 17, 17 plus 3, 20. So your micro instruction format is of 20 bit. So if you see the diagram here, you can see control memory is of 128 into 20 bits. So is it clear now? So 128 into 20. So how it is divided into 20? Your address occupies 7 bits. Your branch field occupies 2 bits. Your condition for branching occupies 2 bits. Your F3 field 3 bits. F2 field 3 bits. F1 field 3 bits. So total 20. So because we're discussing about control memory. So control memory is of 128 into 20. So the divisions are like this, 20 bits, right? Now we'll discuss each one. What is AD, what is BR, what is CD, and what does this F3 contains. So if you say F3 field occupies 3 bits, that means 2 power 3 will get total 8 instructions. Okay. Now we'll see. Yeah, if you see here, micro instruction field descriptions. So as we said that we have three types of field descriptions: the F1, F2, and F3. Okay. So F1. So here F1. As we said, that F1 contains 3 bits, F2 contains 3 bits, and F3 contains 3 bits. So 3 bits in the sense 2 power 3, 2 power n, that is 2 power 3, we get 8 micro operations. Okay. So for F1, we have 8 micro operations, F2, we have 8 micro operations, and for F3 also, we have 8 micro operations. So for F1, so 8 in the sense it will start from 0 to 7. So 0, 0, 0, 0, 0, 0. We don't have any micro operation, which is none. We call it as NOP, that is no operation. So 001 is add, that is accumulator is added with the data register, and the result is stored in accumulator, that is add. So and the 010, so 010 is a clear accumulator. So if you see here, so this is 0, right? So this is 0, so this is 1, okay, so this is 2, like that. Okay, so CLR AC means clear accumulator. So now next is increment accumulator. Okay, so here if you see F1 field, it mainly focus upon if you see F2 subtraction, addition, arithmetic operation. If you see F3 shift operations, so arithmetic logical shift micro operations, that's a combination, as we know. So F1 is logical micro operations, so F2 is arithmetic operations, and F3 is shift operations. So if you see 0011, that is 3, that is INC AC, that is increment accumulator. So AC plus 1. If you see DRT AC, so data register to accumulator. So data from data register goes to accumulator, that is 100. So if you see DR to AR, so data register to address register. Okay, so data register occupies 0 to 10 bits, and it goes to address register. Next, PCTAR. So PC2, that is program counter to address register. Okay, so PC to AR. Next is write. So write operation is we are writing into address register. So DR tends to M of AR. So this is all about F1. So now if we see F2, so F2 as we said, it is also 3 bits. So 2 power 3 we'll get 8 micro operations, right? So 000, 001, 010, 011, 100, 101, 110, 111. So if you see in the 3 cases, the first one 000, it contains no operation. Okay. So next 001 is for subtraction, that is accumulator minus data register, and the result is stored in accumulator. And 010 is OR, AC or DR, and 011 is AND, AC and DR, and the result is stored in accumulator. 100 is read. So read micro operation, that is here in F1 we got the last one is write operation, and in F2 we get read operation. Okay. Next 110 is nothing but your data register is incremented to 1. So DR plus 1 tends to DR, that is increment DR, and 111 is PCT DR, that is a program counter to data register, that is 0 to 10. And finally we have F3. So F2 is over. So finally we have F3. So as we said that the first one 0 is always no operation, NOP. So 001 is for XOR operation. So that is accumulator XOR data register, that is stored in accumulator. So 010 is complement, and 011 is shift left. Okay, shift left accumulator. 100 is shift right accumulator, and 101 is increment program counter, and 110 is ARTPC, that is accumulator, sorry, address register to program counter. And finally 111 is for reserved, so we can't use it. Okay, so in this way we divided into 3 fields, F1, F2, F3. So in most cases, if you see the diagram here, from arithmetic logical shift unit, it goes to here control memory, that is 20 bits. So 20 bits is divided into fields, and that too we focus upon F1, F2, F3. So which is of 3 bits. So we'll get a 2 power 3, 8 micro operations. Okay. So next is CD and BR. So CD is so what we discussed for CD. So CD is the condition for branching, and BR is for branch field. So if you say CD, so how many bits does it occupy? So CD occupy 2 bits and BR also occupy 2 bits, right? So 2 bits in the sense 2 power 2 will get 4 micro operations. So if you see, we got 4 micro operations here, and for BR also we got 4 micro operations. So coming to CD, so first we have 4 micro operations, that is 0 0 0 1 1 0 1 1. So the symbol for the first one is U, that is unconditional branch, and second one is I, that is indirect address bit, and third one is S, that is sign bit of accumulator, and the fourth one is Z, that is 0 value in accumulator. So as we know that whenever the condition is always equal to 1, we go for unconditional branch. So what is unconditional branching here? For example, if we specify any condition, for example, if we hit the 100th memory location, you jump to that 150th particular location. If you say that, that is conditional branching. So if you not specify any condition here, and if you want to without any condition, if it jumps from one location to another location, so we simply call it as unconditional branch, and it is denoted with the symbol U. So we know what indirect addressing bit is. So indirect addressing bit is always the 15th bit. Okay, so 0 to 10. So 0 to 10 is for address, 11 to 14 is for opcode, and 15th bit is your indirect address bit, right? And sign bit of AC. So S stands for sign bit of AC, that is accumulator, that is 15th bit. Okay, so this sign bit decides whether it is a positive sign or negative sign. So if accumulator value holds a 0 value, which is nothing but Z, okay, 0. So that's all about CD. And coming to BR, so here BR we again have the 4 micro operations. The first one 0 0 is for jump, 0 1 is for call, 1 0 is for return, 1 1 is for map. Okay, so first jump. So from address register to control address register if condition equal to 1. If condition equal to 0, we increment control address register. So control address register we increment to 1. If control address register is 0, and in the next case, if the condition equal to 0, control address register becomes 1. So coming to call, that is 0 1. So here, if condition equal to 1, your control address register is incremented to 1, which is sent to subroutine register. So where your routines will be checked. If you see here, we have different routines, right? So here add routine, unt routine, LDA routine, STA routine, BUN routine. So who are going to do this routines? Your subroutine register, and from address register address it goes to control address register. So if condition equal to 0, then there is no case of SPR comes into picture. So simply CR plus 1, and the result is stored in CR. And the next one return, RET. So return from subroutine. So SBR to CR. And finally map. So map is nothing but your 0 1 6 bits are from 0 to control address register 0 1 6, and data register as well from 11 to 14, that is opcode, right? So 11 to 14 tends to CR 2 to 5. So this is micro operations for CD and BR. Okay, so the next is symbolic micro instructions. What is symbolic micro instructions? So symbols are used in micro instructions as in assembly language. So the main agenda of symbolic micro instructions is binary equivalent by a microprogram assembler. So these micro instructions are translated into binary equivalent. Okay, so it contains 5 fields. So if you see carefully, a label, so semicolon micro operation, semicolon CD, semicolon BR, semicolon AD. So what is label here? So label may be empty or may specify symbol address terminated with a colon. Okay, so what is a label here? It may be empty or it may specify a symbolic address, right? So next is micro operation. So what is micro operation? So micro operations can be addition micro operation, arithmetic micro operation, shift micro operation. So whatever the operations it is, but it is separated with commas. So next is CD. So what is CD here? Condition, right? So one of UISZ, we already discussed about these 4, unconditional, indirect address bit, sign of AC, 0 value in AC. So next is BR, one of BR. So we already discussed this: jump, call, return, map, and finally AD. AD is nothing but one of the symbolic address. Okay, so next is empty. So these are the 5 fields present in the symbolic micro instructions. So this symbolic micro program contains the fetch routine. So what is the fetch routine here? What is instruction cycle? Fetch, decode, execute, store. Again, fetch, decode, execute, store, which is nothing but your instruction cycle, isn't it? So during fetch, we'll read an instruction from memory and decode the instruction and update PC. So what's happening during fetch? we are getting an instruction from the memory, and finally we are decoding that instruction and we are updating the PC. For example, if PC is pointed to the first address location, the next PC should always point to the current location, right? So PC then increments to 1. Now PC becomes 2. And in the next case, PC again increments to 1. PC becomes 2. So if you see the sequence of micro operations which are to be followed in the fetch cycle. So first, program counter to address register is the first step. Program counter to address register. So we're getting from the address register. So your PC will increment to 1. So that's what we said. During a fetch instruction, your PC will increment to 1. And M of AR, that at the memory location of that address register, which is sent to the data register. So what data is present in that address location, we'll get that. Okay. And finally, control address register, which is a control unit. Okay. And data register 11 to 40, that is a opcode to CR2 to 5. And the data register 0 to 10 is sent to address register. So this is what exactly happening in fetch cycle. So symbolic micro instruction for the fetch cycle. So that's what we're doing for fetch. Okay. So ORG means origin. So it starts at 64, right? So next to PC to DR, you can see here. PC to AR, this is the first step. So first it starts at origin 64th location, PC to AR. Okay, so next is jump. Next it goes to the next location. So next is read. So we are reading M of AR to DR is nothing but read, and we are incrementing PC. So read comma INC PC. INC PC means increment PC. Again next. So finally we are what are we doing here? DR to AR. So DRT AR, that is mapping. So finally we are mapping, right? So these are the binary equivalents translated by an assembler. For example, 1000000. Okay. So your address is this is 7-bit. This is 7-bit. This is 2-bit. 2-bit. 333. So in this way we can get the binary equivalents translated by an assembler. Okay. So this is a symbolic microprogram. So it's a control storage is 128. As we discussed, it contains 20 bits. So 20 bits like 7, 2, 2, 7 plus 2, 4, 9, 9 plus 2, 11, 11 plus 3, 14, 14 plus 3, 17, 17 plus 3, 20. Okay. So the first 64 words, routines for 16 machine instructions. The last 60 was total 128, right? So 128 words. In that first 64 words contains routines for the 16 machine languages instructions, and the last 64 words used for other purposes. Okay, so these are the partial symbolic microprogram. Add, so different for branch, for over, for store, for exchange. For add, it starts at origin 0. For branch, it starts at origin 4. For store, it starts at origin 8. For exchange, origin 12. As we said, for fetch, origin 64. Okay, this is for indirect. So for origin 0, so next is no operation. So there is I, so indirect addressing. So for indirect addressing, there is no operation. So next is read, so unconditional branch, add, unconditional. So if it is unconditional, it's nothing but jumping. Okay, so CD, we call it as U. For branch, we call it as jump. The address level is we are going to the next address. And here we are fetching. Okay, so in this way, we'll denote all the symbolic microprograms. Okay, so that's all about this topic. In the next class, we'll discuss about design of a control unit. So the students who are watching my channel for the first time, I request you to please subscribe my channel and please share my videos to your friends and well-wishers, and please support my channel in all possible ways. Thank you. Thank you very much and have a wonderful day.